Okay, so we've got the CH4 molecule, which is definitely nonlinear, and the N2 molecule, which is linear. And we want to know, first of all, which one has a greater average translational kinetic energy at a certain temperature. So if we want to know the translational kinetic energy of one molecule, this also goes into the idea of modes. But for translational kinetic energy, we don't look at all the modes. We're only going to look at the relevant modes. Like, for instance, this CH4 molecule has lots of modes, but how many of those modes count as translational kinetic energy?
For the polyatomic?
Yeah.
Or
really for any type of molecule. How many translational modes would one molecule have?
3.
Yeah, because it can move in 3 dimensions. So if we care about translational kinetic energy, we would look at just the 3 translational modes and ignore the other modes. We don't care about whether or not this molecule is rotating. We don't care whether or not the individual atoms are vibrating against each other. If all we care about is the translational kinetic energy of the molecule, we're going to focus on just those 3 translational modes. And how much energy does each mode have? Or how would you usually write out energy of one mode?
It's 1/2 kBT.
Yeah. 1/2 kBT is the energy per mode. And we know the temperature here is 1,000 Kelvin. So we could fill in 1,000 Kelvin for T. We could fill in the usual value for Boltzmann's constant. I'm just going to leave it in this format for now, though.
Okay.
So that's the energy in one mode. How would we figure out how much energy is in the form of translational kinetic energy overall?
Do you find out how many molecules there is? And
if we wanted the total energy, yes, but this isn't looking for the total energy. It's just asking for the kinetic energy of one molecule. Because it's talking about the average KE of a single molecule.
Do you multiply it by 3 since it has the 3 modes?
Yeah, there's 3 modes that we care about, the 3 translational modes of this one molecule. We know each one has this much energy, so we just multiply that much energy by 3. KE of one molecule is going to be 3 times that formula, 3 times 1/2 kBT. In other words, 3/2 kBT. So 3/2 times Boltzmann's constant times the temperature, 1,000 Kelvin, is the translational kinetic energy of one CH4 molecule on average. If we did the same approach to the nitrogen molecule, would anything be different?
Yeah, it would only have 2 oh no, because it would have 3.
Right. It's still got those same 3 translational modes because this one can still move in 3 dimensions. So that means we should expect the same number of translational modes. And therefore, the kinetic energy of the nitrogen molecule is also going to be 3/2 times Boltzmann's constant times 1,000 Kelvin. So it looks like these 2 molecules will, on average, have the same kinetic energy, same translational kinetic energy. They're going to have different amounts of other energies. Like, for instance, the CH4 is going to have more rotational energy because it has more rotational modes. But the translational kinetic energy of each molecule should be the same.
Does it matter that one has more moles than the other?
No, because we're just looking at the average energy of one molecule. If we were looking at like the total thermal energy of this sample and the total thermal energy of this sample, then the amount of moles would definitely matter. But in this case, we're not looking at the whole sample. We're looking at just one average molecule of CH4 and one average molecule of N2. So it doesn't matter how many other molecules there are. We're focusing on just the behavior of one average molecule.
Okay.
Any other questions on that so far?
Oh no, I'm looking at E, or I guess for D they would have the same translational speed, right?
Well, they have the same kinetic energy. Does same kinetic energy have to mean same speed?
By the way you phrase that, I'm gonna go with no.
Okay, but why though? What I mean, what's your usual formula for kinetic energy?
Um, it's the mv squared, right?
Yeah, 1/2 mv squared.
Or one, yeah.
So we know they have the same kinetic energy, but that doesn't mean they have to have the same speed, because what else is different about these two molecules?
The mass.
Right, they've got very different molecular mass. So, and of course, if they had the same mass, like let's say you had two of the same type of molecule and they're at the same temperature. Same temperature guarantees the same kinetic energy per molecule. If they're the same kinetic energy and also the same mass, that would mean they are the same speed. But if they're different masses, how would you be able to tell which one has a faster speed?
The one, would it be the one with the bigger mass would have more speed?
Bigger mass, they got to be the same kinetic energy though. So more mass means
Oh,
you
you
have to
said it
have,
equal.
yeah, exactly. We can write it out as we could say kinetic energy 1 equals kinetic energy 2. Therefore, 1/2 m1 v1 squared equals 1/2 m2 v2 squared. And you can multiply both sides by 2 to get rid of the 1/2s. So we just get m1 times v1 squared equals m2 times v2 squared. So what are
So,
we going to have? Sorry, go ahead.
because we're looking for the velocity, right? So if the mass is bigger on the one side, then the velocity has to be bigger on the other for it to be equal.
Right. You could have, for instance, a large mass times a slow speed squared, balancing out a small mass times a fast speed squared. So whichever one of these is less massive is going to be the faster speed. And when we're talking about mass here, we're still talking about the mass of one single molecule. So we'd have to compare the molecular mass of one CH4 molecule and the molecular mass of one N2 molecule. And how would we get information about those masses?
Periodic table.
Yeah, you could just look up carbon, hydrogen, nitrogen on the periodic table. And of course, N2 is going to be the nitrogen mass times 2, because there's 2 of them, and then carbon mass plus 4 times the hydrogen mass. And then whichever one of those is less massive is going to have a faster speed. In fact, you could even plug in the molecular masses and solve for one speed in terms of the other. Figure out like this one is not just going faster than the other one, it's going this much times faster than the other one. So you could actually get a ratio of the speeds. Any other questions on that so far?
No, that explained it. Thank you.
Mhm.
But okay, so for question or 2B, it's
Mhm.
asking if either has the greater number of active modes at 1000 K.
Mhm.
CH4 would have the more active modes because it's not just asking for translational. So that means that at a
Mhm.
higher temperature, it's not linear and it has the vibrational, rotational, and translational.
Yeah, because this is asking for all the active modes, as you said, not just the translational ones. And 1000 Kelvin, I would expect to be hot enough that it would have all the modes active. I would presume none of them would be frozen out. In fact, I think we can even see this from the graph we have up here. At 1000 Kelvin, well, I guess some of them might be frozen out because it looks like these graphs are still on their way up.
Mhm.
We can definitely see that at 1000 Kelvin, N2 is down here and CH4 is way up here. So at 1000 Kelvin, CH4 has way more modes than N2 does. And as you said, that's because we're getting, first of all, 3 rotational modes instead of 2 because it's nonlinear. And also it's at least starting to activate some of its vibrational modes. So yeah, the CH4 is definitely going to have more modes than the N2 does.
Yeah. Okay, cool.
Any other questions on that one?
I think I'm good on that one.
And then part E, I think, is getting into kind of getting into the idea of heat capacity. We're talking about adding heat and getting the temperature to change. The thing is, though, if you add heat to this, what's going to happen to a sample if you add heat? What happens?
It'll start to vibrate.
Well, I mean, they're already vibrating, but it's going to at least make them vibrate more because the modes get more energy. And I think this goes back to the equipartition theorem. We're adding some heat. According to the equipartition theorem, how does that heat get distributed?
Equally between KE and PE,
Um,
or just between
I,
the KEs?
I would say just between all the modes. If it's
Yeah.
a solid, specifically a monoatomic solid, then half the modes are kinetic and half the modes are potential. So it would get evenly split amongst kinetic and potential. But more generally, for any substance, if you add some energy and it reaches thermal equilibrium, then the energy you've added gets distributed evenly amongst all of the active modes. That is, all the modes that are not frozen out. So that means that we're raising the energy per mode, and energy per mode ties into the idea of temperature as well. In fact, we start at 1,000 Kelvin, we add some heat. Would you expect one or the other of these to raise its temperature by more, or would they raise their temperatures by the same amount?
I would. I think the raising it would be different because one has more mass, right?
They do have different masses. The thing is, though, if you wait long enough, what would you expect to happen to the temperature of the whole sample?
It'll reach equilibrium.
Right, which means everything, the CH4 and the N2, are all at the same final temperature.
Okay.
And they both started at the same initial temperature. We're assuming that assuming you wait long enough, they're all reaching the same final temperature. So everything's going to go through the same change in temperature here. And this is kind of a tricky question here because it seems to be hinting that you're adding heat to them and you're trying to calculate which one changes temperature more. But I think the key here is it's not saying we're adding an amount of heat to the CH4 and we're adding an amount of heat to the N2. If we were adding the same amount of heat to each sample separately, then they would change temperature by different amounts. Because the same energy doesn't mean the same change in temperature.
Yeah, I think that's what I got caught up on. I thought they were like in different containers for a second.
Exactly. If they were separated, if they were in different containers, then that would very much be a concern. Adding the same amount of energy to both containers would lead to different temperature changes. But in this case, it says it's a gas mixture. So I would interpret that as the CH4 and the N2 mixed together, which means if we're adding heat, we're not separately adding heat to the CH4 and adding the same amount of heat to the N2. We're just adding heat to the container that's got both of them mixed together. So I would expect that the energy is going to get evenly distributed and the whole system should reach thermal equilibrium pretty quickly. Any questions on that so far?
So does that mean they would have the same temperature change?
Yeah, I would expect so, because the whole sample starts off at 1,000 Kelvin, and the whole sample is going to end at another final temperature slightly higher than 1,000 Kelvin, maybe, I don't know, 1,003 Kelvin or something. But because it's all mixed together and presumably all able to exchange heat rapidly with itself or with the other molecules in the same sample, then I would expect the energy to get evenly distributed. So the final temperature of everything is all the same as each other.
So it's just a trick question, pretty much.
I don't know if I'd say a trick question, but sort of designed to get you thinking about the difference between adding heat to each sample separately versus adding heat to the whole thing.
Okay.
On the other hand, if we did add heat to each substance separately, then the number of modes would make a big difference there. Because if you're adding the energy to, actually, let's take a quick look at the number of modes. Let's assume for the moment that everything is active, which is not quite true at 1,000 Kelvin, but let's suppose we're at a much higher temperature, so all the modes are active. The nitrogen, the N2, is going to have the 3 translational modes, 2 rotational modes, but also at high temperatures, what else would it have?
Vibrational.
Right. And how many of those would you expect?
2.
Right. For diatomic, it's just going to be 2, if they're even active at all.
Can you explain? I just know that because it equals 7.
Mm-hmm.
And it's just vibrational because I'm not too sure why it's only 2.
Specifically, if you take a look at what's going on inside the molecule, like the whole molecule could be moving around or could be rotating. So those would be the 3 translational and 2 rotational. But if you take a look at what's going on inside the molecule, the individual atoms could be vibrating against each other. And as they vibrate, based on the Lennard-Jones potential graph we've seen, the bond acts almost like a tiny invisible spring. However, that's just one dimension, that's just one single spring, so one dimension worth of vibration. These atoms are vibrating against each other along a one-dimensional oscillation. And one-dimensional oscillation means they've got one mode of kinetic energy moving along that direction, and also one mode of potential energy interacting with each other along that dimension. So the vibration inside the molecule can be accounted for by one kinetic energy mode and one potential energy mode.
Okay.
2 internal vibrational modes. For larger than diatomic, it gets more complicated because we've got to take into account the interaction of each hydrogen atom with the central carbon atom, and the interactions of the hydrogen atoms with each other as the bonds flex a little bit. So it gets way more complicated to visualize. But fortunately, there's a very clever mathematical trick for figuring out the number of modes total without even having to worry about what specifically is vibrating. And one way to do this is to visualize or to run calculations comparing what we'd expect for the whole molecule versus what we'd expect for dealing with individual atoms on their own. Like if we take a look at the whole molecule here, if you just treat this whole molecule as just one big sort of pyramid-shaped lump, how many modes would you expect that lump to have?
I'm not sure. I would guess 4 because they're connected at 4 points.
Well, ignoring what's going on inside, let's say you just have, so ignoring what's happening inside, let's say you just have this pyramid-shaped lump. This pyramid-shaped lump that is drifting around in space, ignoring the atoms inside the lump, how many ways can this lump have energy?
6?
Yeah, because it can move in 3 dimensions and it can rotate in 3 dimensions also because it's nonlinear. So we should expect 3 translational modes and 3 rotational modes. And note that those all count as kinetic energy. Translational motion is kinetic energy. Rotational motion is also kinetic energy. So based on the whole molecule, we should expect 6 kinetic energy modes for the whole molecule. Or I shouldn't say expected, let's say counted so far, because there's going to be more kinetic energy modes if we take a look inside. But based on the whole molecule, we have counted 6 kinetic energy modes so far. But if we now take a look at what's going on inside, if we look at the individual atoms within the molecule, if you take a look at one atom, like let's say this one hydrogen atom, how many kinetic energy modes would you expect that one hydrogen atom to have?
1.
It's able to move in how many dimensions though? If you,
yeah, 3.
Right. If we treat this hydrogen atom as just moving on its own, it's able to move in 3 dimensions. So we expect each individual atom to have 3 translational kinetic energy modes each.
And that's kind of looking at the graph too with the monatomic gases having 3.
Yeah, each individual atom, and really whether it's bonded or not, we should expect each individual atom taken on its own to have 3 modes, 3 kinetic energy modes, and potential energy modes also because it's interacting with other atoms in the same molecule. But looking at kinetic energy alone for now, this atom should have 3 kinetic energy modes, and so should every other atom in the system. And in this molecule, how many atoms are there?
4.
Right.
Or, yeah, 4.
4 hydrogen atoms, but also...
so 5.
Yeah. So we got 3 translational kinetic energy modes for each atom and 5 atoms in the molecule. So if we got 5 atoms and each one has 3 kinetic energy modes, how many kinetic energy modes should we expect overall?
15.
Right, 15 kinetic energy modes expected. So looking at the individual atoms, we expect 15 kinetic energy modes for this molecule. How many kinetic energy modes have we counted so far, though, looking at the whole molecule?
21.
These aren't added together, though, because we've counted, looking at the whole molecule, we've just counted the 6 originally. We had, looking at the whole molecule as if it were just one solid object, we had 3 translational modes, 3 rotational modes. So we've counted 6 kinetic energy modes so far. But according to our individual atom analysis, there should be 15 kinetic energy modes. We've only counted 6 of them. So how many are left unaccounted for?
9.
Right. So those mysterious extra 9 modes, what do you think those extra 9 modes are? They're not translational, they're not rotational.
Vibrational.
Yeah. And since these are specifically kinetic energy, that means there's 9 kinetic energy vibrational modes. But there's also potential energy vibrational modes. These 9 are just talking about how the atoms wiggle around inside the molecule. But the atoms are also interacting with each other inside the molecule. So there's also the same number of potential energy vibrational modes. The 9 kinetic energy vibrational modes basically means that this molecule acts like there's 9 tiny invisible springs inside it. Each one of those tiny invisible springs has kinetic energy and potential energy. So if there's 9 kinetic energy vibrational modes inside the molecule, there's also a matching 9 potential energy vibrational modes. So now that we know that, we can add those in to the whole molecule. We've got 6 kinetic energy modes counted so far, plus 9, I guess we should just combine those, 18 vibrational modes. So 3 translational for the whole molecule, 3 rotational for the whole molecule, and we now know 18 vibrational modes. There's 18 different ways these 5 atoms can have energy inside the molecule. For a total of, looks like 24 modes total for that whole molecule. So that is generally, or at least this is one way you can calculate the total number of modes for a molecule in a gas anyway. If we're assuming they're all active.
Yeah.
And this should generally be true, not just for CH4, but for any 5-atom molecule that's nonlinear.
And so,
should apply.
Sorry. And so if it was frozen out, it would only be 6.
In fact, it might even be only 3. If you're at very low temperatures, the vibrational modes and rotational modes will all be frozen out. So you'd only have the 3 translational modes and that's it. At more medium temperatures, maybe about room temperature, we should expect the rotational modes to also be active. So we'd have 6 modes.
Okay.
And at very high temperatures, we'd have all 24 modes active.
Okay, got it.
And we can generalize this also, because in this case, we got the 15 because it was specifically 5 atoms. But more generally, let's say, let's try generalizing this. Let's say instead of having 15 modes, let's say we had, or instead of having 5 atoms, let's say we had n atoms. Can I do that? So let's say we had n atoms. It doesn't really look very good.
That's okay. I mean, I can see it.
Yeah.
Well, now it's 5, but.
Okay, so we have n atoms. Then instead of having 15 kinetic energy modes, we'd multiply 3 times n. And so we just have this arbitrary 3n. So let's say 3n is the number of kinetic energy modes we would expect. We've already counted 6. So how would you figure out how many leftover extra modes they are?
3n minus 6.
Right. So we're going to have 3n minus 6 extra kinetic energy modes uncounted, and those are the vibrational modes. And of course, there's also 3n minus 6 vibrational modes or potential energy vibrational modes as well, because the kinetic energy vibrational and potential energy vibrational have to match. So combining these together, if we add up, we had 3 translational, 3 rotational, and 3n minus 6 plus 3n minus 6 would be 6n minus 12 internal vibrational modes, for a total of, the 3 and 3 is 6. That partially cancels out the negative 12. So 6n minus 6 modes total. So this generalizes it. Now, in general, we can expect a polyatomic molecule to have 6n minus 6 modes. One caveat, though, what shape were we assuming this was?
Pyramid.
Yeah, or more broadly, nonlinear. It doesn't really matter exactly what shape it is. All we really care about is it a straight line or not? And since this was definitely nonlinear, that means we were able to assume 3 rotational modes. So the calculations follow when we get 6n minus 6. So generally, any nonlinear polyatomic molecule, if all the modes are active, it's going to have 6n minus 6 modes, where n is the number of atoms in the molecule. If it was linear, though, what difference would that make? Yeah, we'd have the 2 rotational. So if it is linear, then this 2 would be replaced by, or this 3 would be replaced by a 2. So instead of 3, we'd have 2 rotational modes. And then we carry that through as well. Instead of deducting the 6 already counted, we'd only have 5 already counted. So we'd say we've already counted 5 from the whole molecule, which means instead of 3n minus 6, we'd have 3n minus 5. So if we wanted to run this same analysis for linear, because what we had was nonlinear polyatomic. If we try doing the same thing for linear polyatomic, that is linear in shape, we've still got the 3 translational. We've got only 2 rotational. And instead of having 3n minus 6 plus 3n minus 6, we'd have 3n minus 5 plus 3n minus 5. So 6n minus 10 internal vibrational. Add all those up, and what do we get?
6n minus 5.
Right. So that would be the formula you'd use if you want to know the total number of modes, if they're all active, for a linear polyatomic molecule. And that covers everything. You've got polyatomic linear molecules, polyatomic nonlinear shaped molecules, and of course, monoatomic is just going to be 3 translational modes, and that's it. So those cover all the possible cases.
Okay.
In fact, this even works for the diatomic one. If we just plug in, like for diatomic, what's the n value? What was n supposed to represent in the first place?
The number of atoms.
Right. Diatomic is just 2 atoms. And would you call that linear or nonlinear?
Linear.
So we'd use the 6n minus 5. So that'll be 6 times 2 minus 5. In other words, 12 minus 5, which is 7. In other words, exactly what we got when we counted it up by hand. So this formula correctly predicts the number of modes we should expect for a diatomic molecule anyway. And it generalizes it to being able to find the total number of modes for any size molecule. No matter how big or how small the molecule is, if you just count up the number of atoms of any type in the molecule and use that for n, 6n minus 6 or 6n minus 5, depending on the shape, will tell you the total number of modes in that molecule, assuming they're all active.
Okay, cool.
Any other questions on that so far?
Oh, I was wondering, is there like a certain order of modes that gets frozen out, if that makes sense?
Yeah, in terms of at different temperatures.
Yeah.
Typically, I would expect the translational modes to always be active, no matter what the temperature is, because the atoms can always move around. The only exception would be if they're at absolute zero, then we would expect the particles to not be moving at all, but that's not really going to happen. But as long as the particles are able to move, which is basically always, you're going to expect 3 translational modes. Unless it's in like a hypothetical 2-dimensional universe, then it would only be 2 translational modes. The rotational modes I would expect to be frozen out at very low temperatures, like extremely cold. But once you get up to about room temperature, I would expect the rotational modes to be active. The internal vibrational modes I would expect to be frozen out until you get up to very high temperatures, though. And in fact, that's really what this graph up here is all about. That the increase on the graph, we've got a graph where the horizontal axis is temperature, the vertical axis is listed as heat capacity over R, but that's basically half the number of modes per particle. So for instance, 7.5 on this axis, that's half the number of modes, so number of modes would be 15 here. But this rise in each one of these graphs, as we increase the temperature, we're increasing the number of modes that are available because we're unfreezing the modes. And for any given molecule, that's going to be an all at once thing. There's going to be some temperature shift where this molecule goes from vibrational modes frozen out to vibrational modes are active. So really each one of these should be going from like 3 jumping up to 5, jumping up to 7. But this isn't talking about individual molecules. This graph is talking about for a large sample. So as you increase the temperature, maybe you've got all the molecules at the low energy state, and then some of them have enough energy to jump up to the next energy state until eventually they're all at the next energy state. But if you look at it on average, the average is gradually increasing as more and more molecules start to vibrate. But for instance, for a single diatomic molecule, it's going to be either at 3 or 5 or 7. The in-between values don't really work. But the average could be anywhere between 3 and 7, depending on how many of the molecules are vibrating. Any other questions on that so far?
Oh, and also, did you determine that CH4 was nonlinear based on its chemical structure?
Yeah, and this is really bringing in extra knowledge from chemistry. The problem itself doesn't really specify that CH4 is nonlinear, but I think it's expecting you to either know that from chemistry or to look it up elsewhere. Any diatomic molecule, of course, is going to be linear because 2 points always form a straight line. But CH4, and we can see this from chemistry, that the carbon atom is going to be bonded to all 4 hydrogen atoms. The hydrogen atoms can't really bond with each other because hydrogen can only bond with one thing, and that's the carbon in this case. So the carbon has 4 hydrogens branching off of it. And even if you don't know the exact shape as a tetrahedron, you can still get the idea that it's not going to be linear, because there's no way you can arrange a carbon and 4 hydrogens in a straight line while still having all the hydrogens bonded to the carbon and not to each other. But yeah, generally for the shape of the molecule, we usually need extra information from chemistry.
Oh, okay, that makes sense. Thank you.
But even if it was linear, we would still expect it to have more modes per particle than the N2 does. It would have the same number of rotational modes, but would have more vibrational modes because of the more complicated structure, the larger number of particles. And also, while we're at it, let's take a moment to see if we can use this idea of modes to build up a formula for thermal energy in general. Going back to the idea of energy in the modes, energy per mode was the usual 1/2 times Boltzmann's constant times temperature. But if you wanted to find the energy in a whole molecule, how would you have to modify that? Like for instance, let's say we were taking a look at that nitrogen molecule with 7 modes. We know the energy in one mode is 1/2 kBT. How would you figure out the energy in the whole molecule?
See how many modes are in the molecule.
Yeah, and let's say you have 7 modes. What would you do with that 7?
Multiply it by 7.
Right, multiply energy in one mode times 7, or more generally, times the number of modes. So we've got energy per mode times the number of modes. That is number of modes per particle. And I'm just going to write it as number of modes, but keep in mind that's specifically number of modes per molecule, not necessarily total number of modes. So this would give us the energy, the energy of the entire molecule, not just the translational kinetic energy that we were looking at earlier, but the total thermal energy of the entire molecule in all the modes. Of course, we're rarely dealing with just one molecule. Typically, we'll be dealing with lots of molecules. So if we wanted to figure out the energy in lots of molecules, let's say capital N is the number of molecules. The energy in capital N molecules, we take the energy of one molecule and do what with that?
Multiply it by the amount of molecules.
Right, which in this case we would just call capital N. Usually we use capital N to represent number of molecules. What's probably the most convenient number of molecules to use though?
Avogadro's.
Right, if we use Avogadro's number, that means we're talking about 1 entire mole. So the energy per mole would be that same formula, but with the number of molecules, specifically Avogadro's number, 600 quintillion, or hextillion, 6 times 10 to the 23rd. So this could be used as a formula for the energy in 1 mole. And there's a very convenient substitution we can use. In situations like this, we often end up with Boltzmann's constant, which is very, very, very small, and Avogadro's number, which is very, very, very large, multiplied together. And as a shortcut for that, we use this idea of Boltzmann's constant times Avogadro's number being given its own name. We make up a new constant called R. R is just a substitution for Boltzmann's constant times Avogadro's number. The very, very, very small value of Boltzmann's constant times the very, very large number of Avogadro's number ends up being a much more reasonable number. I think it's something like 8.31 joules per Kelvin mole. And that is in fact the same R you see in the ideal gas equation. So this is the ideal gas constant. And this is a very useful shorthand because instead of having to write out KB and NA and then plug in this ridiculously small number and this ridiculously large number, we just combine those. So the energy per mole is KB and NA combined to just R. And then we've also got, we still have the times temperature, times number of modes, and then the times 1/2. I'll just write that as divided by 2. So R times T times number of modes divided by 2 is a much more convenient formula for energy per mole. Much more compact also. This is, I think, a lot easier to write out and a lot easier to work with than the whole thing from the previous step. And of course, you don't necessarily have to be dealing with exactly 1 mole. You could be dealing with n moles. The energy for, and we usually use lowercase n for number of moles. We just take the energy per mole and multiply by number of moles. So this gives us a very useful formula for the thermal energy of n moles of a gas. In fact, we may as well just call this thermal energy because it's the thermal energy of the whole sample. So very convenient formula for thermal energy of n moles of the sample. As long as you know how many moles there are, the temperature, and the number of modes, you can use this to immediately calculate the thermal energy of the whole thing. Any questions on that so far?
No.
And one other really convenient substitution. Where else have you seen nRT?
The ideal gas law.
Right. So if this is an ideal gas, and of course this formula works whether it's a gas or not, but if it is an ideal gas, there's this other substitution you can make. We can replace nRT with PV. So that means thermal energy would be pressure times volume times number of modes over 2. And this is really convenient in many cases because what we now have is a formula for thermal energy that does not include what? What's not in this formula anymore?
R?
Yeah, we don't have to know what R is, but also what important property of the sample itself is no longer in the equation.
Oh, temperature?
Yeah, and that's really weird because, I mean, temperature is the indicator for thermal energy. Usually to calculate thermal energy, you need to know the temperature. But this provides a way to, specifically if it is an ideal gas, this provides us a way to calculate the thermal energy without even needing to know the temperature. We just need to know how much space the gas takes up and how much pressure it's under, and also what type of molecule it is so we can calculate number of modes. But this allows us to find thermal energy without even needing to know the temperature. So this can be a very convenient way of calculating thermal energy specifically for gases. But the other formula, nRT times number of modes over 2, works for any substance. Any other questions on that formula?
No, not for me.
And if you want to find heat capacity, we can also think of thermal energy as heat capacity times temperature. So try setting those equal to each other. Heat capacity times temperature equals this formula, and solve for heat capacity and see what you get. What's left should be a formula for heat capacity of that sample. So experiment with those equations, see what more you can figure out by solving for one variable, or try to imagine situations where you would know all of these variables except one, and then you need to solve for the other one. Those would all be situations where this formula would be useful. So experiment with that, see if you can find ways to use formulas like this or this general way of thinking on the F&T problems and other practice quizzes. Let me know if you have any other questions, and I will see you next time.
Thank you.
You're welcome.
Thank you.